I'm very happy to be here with you and to participate to the CCT 2025. The title of my presentation is Development of a Process, Development of a process for producing zirconium-rich alkali-resistant glasses containing heavy metals present in fly ashes from municipal solid waste incineration. Let's kick off my presentation agenda. First, I will begin with an introduction, and then I will present the methodology we used for this study just before presenting results and discussion, and then I will conclude. So concerning introduction, we all know that incineration of solids waste produce non-hazardous waste and fly ashes. Fly ashes contain a lot of heavy metals such cadmium, chromium, zinc, or lead, which requires special management. The conversion of fly ashes into stable glasses through vitrification is a method perfectly controlled and allows the retention of heavy metals in the vitreous matrix. Thus, the presence in the composition of glasses of poorly soluble elements such as zirconium makes the vitreous network more solid, slows the kinetics of alteration of the glasses, and improves their durability. So the purpose of this study was to develop alkali-resistant zirconium-rich glasses that could serve for retention of heavy metals coming from fly ash. So for that, we have to propose different alkali-resistant glass composition to monitoring physical chemical parameters of alkali-resistant glasses and to assess the chemical durability of alkali-resistant glass composition containing fly ash in basic media. So the methodology we use, we first prepare 5 glass composition, including 2 alkali-resistant model glasses type Samphil, namely V1, it's a glass without zirconium and without heavy metals, and V2, it's a glass without zirconium but with heavy metals, and 3 glasses of fly ash, V3, which is a glass with zirconium but without heavy metal, and V4 and V5 are obtaining using V3 as a raw material, 30% for V3 and 60% for V5, and suppleting with oxide, silicon oxide, zirconium oxide, and sodium oxide to give them superior alkali-resistant property. V1 glass has a composition similar to Samphil glass with a high content of oxide of calcium. In V1 glass, we have 50% of oxide of calcium instead of 1.5% for Samphil. So this glass represents the basic composition. V2 glass is obtained by introduction into V1 glass heavy metals present in fly ash such lead, zinc, chromium, and cadmium. V3 glass is the composition of Phrygious PFTS1 glass. This fly ash glass is doped with heavy metals. V4 glass contains 30% of V3 glass supplemented with oxide of silicon, sodium, and zirconium oxide to obtain an alkali-resistant glass composition close to the V1 glass. So to get closer of V1 glass, we added 36.3% of silicon oxide, 12.7% of sodium oxide and 16% of zirconium oxide. And the mass percentage of pollutant is then 4.96%. Okay. The V5 glass is obtained in the same way as V4 glass, but with 16% of V3 glass. To get closer to the V1 glass composition, we added 21.6% of silicon oxide, 2.41% of sodium oxide, and 16% of zirconium oxide. The mass percent of pollutant is then 9.92%. So all the glass were synthesized under the same condition. We first mixed precursor oxide and pollutant oxide. And the mixture were put in a furnace rocking at 1,550 degrees Celsius for 1 hour. And when glass were obtained, they were inhaled at 550 degrees Celsius for 8 hours. So glasses were synthesized in a CNRS, it's a laboratory in Orléans, in France, and the order analyzed has chemical composition, differential thermal analysis, structural analysis, or superficial hydration, and surface composition analysis were carried out in several laboratories laboratories in France, as Saclay Atomic Energy Center, but also in Pierre and Marie Curie University in Paris, and also in CNRS at Orléans. So concerning result and discussion, the synthesized alkali-resistant glasses, when we see the figure 1, we can see photographs of alkali-resistant glasses V1, V2, V3, V4, and V5. You can see that the V1 glass is colorless and transparent. V2 glass, which is dark green, shows some heterogeneities. The difference between the two glass, V1 and V2, is certainly due to the presence of heavy metals in V2. V3 glass is black and opaque. V3 glass is black and opaque. V4 glass is transparent green with heterogeneities. The V5 glass, which is also green in color, has areas that are lighter than the matrix on the entire surface of the glass. This phenomenon may be due either to a phase demixation, which occurs when one of the compounds has reached its solubility limits, or at the beginning of a crystallization. Concerning chemical composition of alkali-resistant glasses, we can see that experimental results are in agreement with theoretical results. We can see the difference between the two results are not very significant, because the mixtures are under 1 to 2%. Concerning glass transition temperature, we can see that all the 5 glasses at temperature around 600 degrees Celsius. Concerning structural analysis, we can see that the diffractograms of V1 and V2 shows that the two glasses are totally amorphous. On the diffractogram of V3, V4, and V5, we can see a presence of small peaks in red lines in figure 3. This is the characteristic of alumina. And the diffractogram of V5 glass reveals additional peaks, the blue lines, that is attributed to the zirconium oxide. Concerning superficial hydratation of alkali-resistant glasses, we can see that V3 and V5 are less hydrated glasses compared to V4, V2, and V1. This is probably related to the hygroscopic nature of certain components of the glasses, like silicon oxide or zirconium oxide, which are responsible for hydratation by contact with the ambient atmosphere. So concerning alteration, we can see on figure 5, same image of V1 glasses surface morphology after 28 days of treatment in aggressive alkaline solution at pH 13 at 80 degrees Celsius. We can see that V1 developed on its surface an irregular alteration layer. We note the presence of some precipitate. We also note decalization because we obtain between 4 and 5% of sodium instead of 12% on the reference glasses, and the relative enrichment of zirconium between 17 and 80% instead of 12% in the reference layer. We can also note calcium enrichment precipitate on the surface. Concerning the alteration of V2 glass, we can see heterogeneous alteration layer, including crystals. This crystal is composed of silicon, zirconium, and calcium. We also note decalization between 3 and 5% of sodium instead of 10% in the reference glass, and an enrichment in zirconium between 14 and 50% instead of 11 in the reference glass. And the precipitates are enriched in calcium. Concerning the alteration of V3 glass, we can see that V3 glass is completely opaque. We can also note precipitation of secondary phases, and the chemical analysis of the alteration layer shows that phyllosilicate type secondary phases are very enriched in calcium, 30% instead of 22% in the reference glass. For V4 glass, we can see that this glass is little attacked. We can see no heterogeneity appears on the surface. The composition of the layer reveals that there is an enrichment in zirconium, 80% instead of 11% in the reference glass, and the depletion in sodium, 5% instead of 9% in the reference glass, and in silicon. And the last glass, the V5 glass, we can see this glass is also little attacked. We can note the formation of some secondary phases and the presence of non-crystalline zirconium oxide crystals. The layer is also enriched enriched in zirconium, 16% instead of 10% in the glass reference, and slightly depleted in calcium, 10% instead of 30% in the reference glass. This can be explained by the fact that silicate glasses with high durability possess silica-rich films which are dense enough to protect the glass from further rapid attack. So to conclude, we can say that we have developed 5 glass compositions, including 2 alkali-resistant model glasses, type stem-fill, V1 and V2, and 3 glasses of fly ash, V3, V4, and V5. The chemical white composition of the glasses determined by electron microscopy is in agree with the theoretical percent, although there is a slight difference between theoretical and experimental composition. Differential thermal analysis show a glass transition around 600 degrees for all glasses. The glasses are totally amorph, even through extremely small peaks of alumina can be observed on the V2 and the V3 diffractograms, and zirconium oxide peaks can only be seen on the V5 diffractogram. The same and electron microphore analysis reveal that all the glasses are covered with an alteration layer at pH 13. These alteration layers are enriched in zirconium for V1, V2, V4, and V5 glasses, and depleted in sodium. What we have to return in this study is that V4 and V5 glasses are the most enriched zirconium alteration layers, and also appear to be the least attacked in alkaline solution. Thank you for your attention.